Hello, this is Dr. Mahmoud Al-Odeh, and in this video, I'll be sharing with you a case study for process capability, and this will give you an idea on how you could define the Six Sigma level. ABC Industries manufactures spherical ball bearings, which are supplied to different automobile manufacturers and are used in the manufacturing process of cars. Approximately 1 million ball bearings of a particular type are produced daily. There have been several complaints from customers, automobile manufacturers. These are their customers. The spherical ball bearings were not conforming to requirements, and many of them had to be rejected. A critical criteria used for evaluation spherical ball bearings is the size of the ball bearing. This is a measure of the diameter of the ball bearing in the centimeters. ABC Industries decided to conduct a process capability study to study this criteria, which is the size of the diameter. A Six Sigma expert was assigned to the responsibility of conducting the study. Okay, in this case, I will share with you what you need to do in order to identify the process capability. First of all, this Lean Six Sigma expert know that there's no way that you could measure every product. As you know, they produce 1 million bearings a day. So there's no way that you could measure the 1 million. So therefore, you have to to take a sample of the population in order to generate the result for the rest. Some commonly used terms to describe the sample and the population are the center and the spread. The center point in the data is represent the average. The spread is the dispersion of the data around the center. So just to keep this in mind, when you study the population and the sample, you need to find out what would be the average and the spread around the data, the sigma. All right, so the Six Sigma expert measured the diameter of all the ball rings in the sample produced in one run. They divided the data into 9 ranges. So as you see, they divide ranges, 9 ranges to simplify the things, and which is what you need to do as a Six Sigma expert. You have to simplify things. You need to make things makes sense to others. So simplifying things is one of your roles. So for this case, we divided this into 9 categories. As you see, from 1 to 3 centimeter, from 3 to 5, 5 to 7, 7 to 9, 9 to 11, etc. And then they observed, they found what would be the number of observations. So there are 64 bearings range between 1 to 3 centimeter. And you could put the average for the range, but this is not important. We're looking into the observation. Once you've done the observation, you could do the histogram. You could create a histogram and you could fit the normal distribution on that. All right, now once you look into this, once you have these 9 categories, what you need to do, you need to find what would be the specification, what the tolerances. And the customer decide that we need the tolerances between 5 and 15 centimeter would be acceptable. As long as it's between 5 and 15, this would be acceptable. So you know that anything between 1 and 5 is not acceptable. This is a defect. Anything over 15, that would be not acceptable. So you will see these are in red because these are not acceptable. So the total observation is listed here. And now find the defects in the red area. In order to find the defect per million opportunity, you divide the defects by the total observation times 1 million. So 4581 divided by 499,033 times 1 million. And that would give you a 9180. All right, now on the right side, This is your standard. This is your reference in order to find what would be the sigma. 1, 2, 3, 4, 5, 6 sigma. And this is already established for you. You could look it up in any quality references, in any Six Sigma references. As you remember, the Six Sigma level will be 3.4 defects per million opportunities, and this is calculated. Now you compare the 9180 with this table. You will see that the 91 is between 3 and 4 sigma. We're not sure exactly how what is the sigma level, but we know it's less than 4 sigma. So the process for this company, they're operating at a less than 4 sigma, higher than a 3 sigma. Now somebody will say, okay, well, 9,000 and 6,000, this is close to 4. Yes, it is almost close to 4 sigma, but we cannot consider it as a 4 sigma level. Therefore, we say it's operated and on a level of less than 4 sigma. In this case, you identified. So this is how you identify the Six Sigma and the process capability. Also, something related to that, we need to go over some of the calculation. Defects, some of the terms as well. Defect per million units, or what we call the DPU. The DPU, the average number of defects per units of products. Total number of defects found in a sample divided by the sample size. This is what we call the DPU. The DPMO, defects per million opportunities, that would be the ratio of the number of defects, the flaws in million opportunities. That, if we need to use the equation, total numbers of defects found in a sample divided by the sample size times the number of defect opportunities per unit in the sample times 1 million. For example, here's an example to clarify these concepts. A form contains 15 fields of information. If 10 forms are sampled and 26 defects are found in the sample, the DPMO is equal to 26. This is the defects, the total defects in total, divided by the sample size. We have a 10 sample size because we selected 10 forms, times 15 fields in each form. So 26 divided by 10 times 15 times 1 million. And that would give you 173,333 defects per million opportunities. DPU, the percentage defective. The total number of defects, just one more time to talk about the DPU. We talked about it here, the DPU, the total number, but we need to adjust that to have a percentage. You multiply it by 100%. Defects times the total units times 100. But the DPU is without the 100% because we're not looking into the percentage. Let's take an example. A process produces 40,000 pencils. 3 types of defects can occur. The number of occurrences of each defect is as below. Blurred printing, 36, too long, 118, rolled ends, 11. Total number of defects is 165. In order to find the DPU, that would be 165 divided by 40,000. This is the DPU. Now, if we're talking about the DPMO, the defects per million opportunities, we need to consider that how many opportunities we have. As you know, we have 3 types of errors we could have here. So we need to consider that. Each error is considered a 1 opportunity. So total number of defects times 1 million divided by the total number of opportunities. So if we want to do the calculation, we'll do the 40,000 plus 120 plus 80,000. Okay, where this is coming from. Let's go back here to here. We know that there are there are the number of ways the number of ways each defect can occur on each item. For this product, blurred printing occurred in only one way. So there are 40,000 opportunities. So number one, so we have three types of error. One is the printing, something wrong with the printing, not clear, blurry printing. So this would be a 40,000 opportunities. Then we will talk about the second type, which is the dimension defects. And for the dimension defects, we will have three places. So 3 times 40, because this is the samples, 3 opportunities times 40, that will give you 120. And the roll ends. We have top and the bottom. The top and the bottom. So that would be 2 opportunities for that type of problem. 2 times 40, that would be 80 opportunities. So add these together, 40, which is the printing issue. Second one would be the dimensions, because there are 3 independent places for dimensions we have to consider. And the rolled ends, 40 plus 120 plus 80. That would be equal to 240,000. These are the number of opportunities that we have. The total number of opportunities would be 1 plus 3 plus 2 plus 2. That would be equal 6. In this case, once we apply the DPMO, that would be equal to the total number of defects, which we just calculated, that number, divided by the total number of opportunities to find what would be the DPMO. So total number of defects, 165, which is right here, taken from how many errors we have, 36 plus 118 plus 11, that would be 165. Divide that, multiply that by 1 million, so that would be 165 million, divided by 240,000, so that would be equal to what? 687.5. This is the DPMO, defect per million opportunities. And based on that, you could go back to this table right here and find out what level of sigma you have. In this case, we have around 6,000, so 210 for the 4, 682, 87, 682. So it's this process in particular perform more than 4 sigma. It's closer to 5 sigma. It's closer to 5 sigma, but we haven't reached to 5 sigma. So it's a great tool. It's a great way to calculate the DPMO. This is a great example. Take a look into that. Let me know if you have any question. And an extra question for you is to do the calculation for this. A process produces 1,500 camshafts. 3 types of defects could occur. The number of occurrences of each defect are rough surface, 12. Wrong dimension for vehicle type, 8. Wrong lobe separation angle is 4. Knowing that there are 2 independent places where the dimensions are checked in 4 places area that are checked, what are the defects per million opportunities? I want you to challenge yourself, calculate it, and let me know if you need help. I'm going to leave it here. There's an option A, B, C, and D, and I'll let you know, or let me know in the comment what would be your answer. The last 2 slides for this video is talking about the PPM. It's another concept. Parts per million defects indicates the number of times a defect part will occur in 1 million parts. Okay, how many defects will occur in 1 million parts? This is what we call the PPM. The DPMO matrix reflects the number of defects occurring in 1 million opportunity. To find the ppm, that would be finding the total number of defects divided by the sample size times 1 million. It is important to note that some authors say the ppm and the DPMO metrics are identical. So if we follow the definitions above, however, this would only be true when the number of opportunity for defects is only one part. So there's a slight difference between the ppm and the DPMO. They're not exactly the same. They're different. It's only the same if there's only one opportunity per defect. For example, suppose that 0.23 gram. This is another example. Take a look into example. These are examples, are real examples. You will see it in the exam, in the certification exam. Suppose 0.23 grams of insect parts are found in 25 kilogram of products. In order to find the ppm, that would be 0.23 divided by 25 thousand. Why 25,000? Because we have to have same units, so we have to exchange the kilogram to gram by multiplying by 1,000. So 0.23 divided by 25,000 times 1 million. The ppm in this case would be 9.2. Another screen that I want to share with you to find out what would be the sigma. In this case, in this table you will see some of the concepts such as the ppm, and this came from Minitab. When you do a Minitab, you will be able to do the process capability, and you will be able to find the CP and the CPK, also the ppm. So in this case, what would be the ppm? The actual look into the normal value, the nominal value. This is in the middle. This what would be the one standard deviation, 1Z. CP is 0.35. This is not capable. The ppm is 150,000 as well. This upper control limits and lower control limits, these are the tolerances, but we go with the best estimate, the one in the middle. The first one is the short term, and the other one is for the long term. And if you see there could be a question on the exam, what's the difference between the CPK and the PPK? The CPK is the short term. The PPK is a prediction for the future, what they're expecting to see in the future based on what the values that you have. With that, I'm going to thank you for watching my videos. Please let me know if you have any questions, whether in the comments or if you're one of my students, please send me an email. I would be happy to answer you. Again, keep an eye on these examples. These very valuable examples will help you to pass the Six Sigma level. Thank you so much.